Alright, hello, my name is Josh Wheeler. In this video, I will be doing a derivation of the mass and energy balance. And we are going to take two equations we're going to break down from what I do up here. And we're going to use Python to solve them and plot the water level and the temperature. We're going to do this equation, or this whole relationship of temperature, over a 100-second period. So I'll get into this real quick. So let's go do our notes real quick. So we have a tank. We have some tank that has a cross-sectional area of, let's say a cross-section area is equal to 1 squared meter. And let's write out a real quick relationship. We're going to say that this tank is mixed very well. The constants inside are going to be mixed very well. So let's write notes over here. So the tank's contents are mixed well. All right. So in this tank, we have initial water level. So the height of the water inside is, let's say, give it a variable h, capital H. That's equal to 1 meter. So it's 1 meter high here. So for this question, we're doing this in terms of temperature. Now for our previous question, see these two equations, we did this a sort of similar sort of problem, but we solved in terms of a mass balance and in terms of concentration. But now we're going to be doing this in terms of temperature. So we have the initial water temperature on the inside here is going to be, let's say, a temperature of 300 Kelvin. And this tank has an input, so an input of water at a different temperature. We'll say the temperature of the water coming in, so we'll give it a variable of Tn, temperature in, is equal to 325 degrees Kelvin. And it comes in at a flow rate, Qn, of 1 cubic meter per second. Now, this same tank also let's say it has a hole at the bottom, or a valve or something that's allowing water to leave the system. And let's say that hole allows water to leave at a flow rate, Q out, of some amount of value of alpha times square root of h, where h, like we said up here, we said that h, our height, initial height, is 1 meter. But for this, we're going to be doing a derivation. So to make it easier ourselves, we're just going to leave things in terms of their variables. And when we get on to the coding, we can actually start using the actual values we're going to plug in here. We'll get onto that later. So I'll actually go ahead and say that alpha, in this case, is equal to 0.4. Alpha also is equal to, which is also equal to, so alpha also stands for an area, so our area out, times the square root of 2g, where g is the gravitational constant, and our area out is the cross-sectional area of the hole in which the water is leaving at this flow rate out. But we're just going to leave it in terms, for simplicity, we're going to leave it in terms of our alpha here. And we'll use this value, 0.4, to plug into our code so we can actually solve it numerically and plot out some plots. Okay, so I think we've got all of our initial information out. So we can start off with the mass balance equation. So let's go ahead and say that our mass of the system is equal to the mass coming in minus the mass leaving, or exiting, so mass out. So we can say that, well, we don't have any masses here, but we know that the relationship between mass, density, and volume, mass is equal to density times volume. So we know that we can find density. We can say that density times volume. Well, our volume here is the cross-sectional area times the height that the water is at. This is our volume right here. So we can bring this down here, and we can say that, okay, our density of the system inside times our volume, which is equal to our cross-sectional area times our height, the water inside, is equal to the density of the water coming in times the flow rate coming in minus the flow rate, or the density of the water leaving, so out, times the flow rate going out, which we can go ahead and write the flow rate going out. We actually know what that is. So we say that is the times the alpha times the square root of h. Okay, so like I said before, the importance of saying that our tank is our tank contents are mixed well. So that means that we can say that our densities aren't different at any points here. We can actually say that they are we can assume that our densities are approximately the same value. So let's go ahead and we'll go there and write that in our notes section. So our densities, so the density, so P of the system, or density of the system, is approximately equal to the density coming in, which is approximately equal to the density leaving. So now we know that relationship. We can actually say that these are all the same value. So if every term has a density, we can go ahead and cancel it out. Okay? So we can go ahead and cancel this out here and here. All right. All right, so now we've done that. We want to go ahead and take a derivative of this side and set it in terms of t. And when you take a derivative, so some other important thing to notice is that for this tank, we want to look for constants. So we look up here, this tank, our two variables here, we have our cross-sectional area and our height. Well, we know that with all this water moving in and out of the system here, the cross-sectional area, the actual area of the tank, is not going to change. It's actually, you could say, it is a constant. It stays constant. So when you take a derivative of a constant, it stays the same. It doesn't change anything. So you can really bring this out, this area, this is our constant, and bring it out on the outside and multiply the outside and leave this height in, because it isn't a constant. Our height isn't a constant. It doesn't stay the same. It can change over time. The water level inside can change. So we're going to leave that on the inside here. So some small change in height over time, multiplied by the cross-sectional area, which we brought out, which was a constant, is equal to the flow rate coming in minus the flow rate leaving. And now, to finish this up, let's go ahead and set this by itself over here by dividing this entire right-hand side by the cross-sectional area. And by doing that, this actually gives us our first equation. We're going to have two equations. So our first equation is some small change in height with respect to a small change in time is equal to our flow rate coming in minus our flow rate going out divided by the cross-sectional area. And that is our first equation. All right. So that was our mass balance for the first one here. All right. So now on to the second part of this. We're just going to take a little more time and a little more explaining, I would say. So we're going to do the energy balance. So we know our energy balance. Let's go ahead and write our energy balance equation out. And we're going to actually go ahead and for this, let's write it out actually. So you know that a small change in our mass of the system is equal to the internal energy plus our velocity over 2, or v over 2, sorry, not velocity, v over 2 plus gz. So these two terms here are our potential and our kinetic energy. Sorry, I had a moment there. So our kinetic energy and our potential energy. So this is our left-handed. So the system is equal to our enthalpy coming in plus our v over 2 our kinetic and potential energy terms coming in times a small change in the mass coming in minus our enthalpy leaving plus the kinetic and potential energy terms out and a small change in the mass leaving minus our small change in heat added into it, so our heat added to the system. But in this case, we don't have any heat being added here, so that's going to cancel out. Times our non-flow work. So our non-flow work is a small change in flow work. Now for this particular equation, we are going to want to actually take out and simplify some few things. So we're going to actually ignore a few terms in this, which we would usually keep in here. For this particular equation, we are going to take out and just ignore our non-flow work. We're going to ignore our kinetic energy and potential energy terms. So it's going to simplify to a much more manageable problem. So let's go ahead and do that. Okay. Yeah, so we take this out. Actually, I'll just go ahead and erase this and just go ahead and write down the simplified version of it. So, which turns into a term of small change in the mass of the system times our internal energy is equal to the enthalpy coming in times our small change in the mass coming in minus the enthalpy leaving. And enthalpy is in terms of heat and temperature, which we will get into later. We'll do a substitution here later. So, and the mass leaving, or mass out. Okay. So, now like before, in our first equation, which we got over here, we can go ahead and we don't have any mass values, but like before we substituted and we know the relationship between what mass, density, and volume is. We can kind of do the same thing here. So we can go ahead and say that, let's go ahead actually and divide by, let's do it in terms of t. Let's do everything in terms of t real quick. So divide across by our d of t term. We're going to go ahead and change this in terms of density and volume. So we can bring this down and say, okay, small change in our density of the system times our cross-sectional area. So our cross-sectional area times our height, which is our volume term, times our, now we have an internal energy term, divided by small change in time, is equal to, now this term here and this term here we can go ahead and rewrite that. That's the same thing as, sorry, Hn doesn't change yet, or enthalpy N. You can write this term as our density N times our flow rate N from before, and rewrite this as our enthalpy out times our density leaving times our flow rate out, which is alpha times our square root of our initial height of the water in the tank. And like before, we have our notes up here. We have our relationship between we can say that our densities of the system are equal to the same thing approximately. So we can go ahead and actually cancel those out real quick. It's very similar to the first question. It's going to kind of repeat, and also the other video which we did. So our densities are going to cancel out. And we can go ahead and bring out our area as a constant, as before, and our height changes. So we can go ahead and do that too. And yeah, let's go ahead and do that. So let's just rewrite this real quick so it's a little easier to see. So we have our flow rate in minus our enthalpy leaving or out times our flow rate out. And let's rewrite this as our cross-sectional area times a small change in our height times our internal energy over small change in time is equal to this. Okay, so now I'm going to go off on a little aside here and do a little more explaining on what our internal energy, and explain it in terms of, or actually relate our internal energy and also enthalpy in terms of temperature. And it'll make more sense, so we can rewrite actually a little bit. Our next step after I do this little aside here will be explaining our internal energy and rewriting an equation. A new equation which we can plug back into here and solve for our final equation in a little bit. I'll explain in a second. So let's go ahead and write our little aside here. So we can say that a small change in enthalpy is equal to our heat capacity at a constant pressure with respect to temperature plus some dependence. So our dependence in this case are 2 times our enthalpy over 2 times our pressure times a small change in pressure, and a small change in internal energy is equal to a similar equation, a heat capacity at constant volume with respect to temperature plus its dependence, which are also kind of similar, a 2 times U value over 2 times volume, and that is times a small change in volume. For this particular problem we're going to be doing, we want to go ahead and just ignore our dependent values. So we're just going to go ahead and ignore them. So this is actually this little relationship here relates our a small change in enthalpy and a small change in internal energy in terms of their heat capacities. So for each one of these, our heat capacities are in respect to a constant of different thing. For instance, for our enthalpy, a small change in enthalpy is equal to a heat capacity held at a constant pressure. And for internal energy, it is with a heat capacity at a constant volume. So now we can, using this relationship, we can rewrite an internal energy equation and go ahead and, I'll go ahead and write that out for you. So let's say that internal energy at some temperature, we don't know what that temperature value is, we can choose any temperature value, minus some internal energy at a reference temperature, or some reference temperature, which to make our life easier, let's just say a reference temperature is 0, is equal to, so for, like I said before, a relationship, we know that for internal energy, the heat capacity is at a constant volume times our temperature, some temperature which we choose, minus some reference temperature, which we're going to say is 0. So we can go ahead and rewrite this equation as so you can write this, and this is 0 as well, and say that internal energy at some temperature is equal to the heat capacity at constant volume times a temperature. Okay, so now we can take this and plug it up here into this equation and start simplifying that down. So let's go ahead and do that. Let's rewrite this equation down here below. So we can rewrite this as our cross-sectional area times a small change in height, and we're going to rewrite, so now we know that our U, our internal energy, is equal to, we can really actually say this is the same thing. So this variable, these two variables are the same thing at a certain temperature. So we can substitute our new relationship of our heat capacity constant volume times the temperature, that temperature up here, and say that, so our cross-sectional area times a small change in our height times our heat capacity at constant volume times the temperature over a small change in time is equal to, now like I said before, this is enthalpy. This is in terms of heat. So we can actually say that this heat, we can rewrite it in terms of a temperature. So we can say that this enthalpy in, why don't we say that our enthalpy in is equal to, let's do it for our notes, and say that our enthalpy in is equal to our temperature in. And that can actually give us a value instead of just leaving it as just a variable, which we have nothing for, we'd have to solve for. We can actually give it a number which we can plug into our code, make it easier for us later. So let's say that our temperature in times our flow rate in minus our H out. Well, we can say that our H out, or enthalpy out, is the same thing as our temperature out. And we can think of our temperature for this tank. We know that there's a difference in temperature when it comes in to the temperature that is inside the tank. But you'll notice here that when the water leaves, there's no indication that there's any change in temperature from when the water leaves this tank to from the water is in the tank to when it leaves. There's no change. So you could really say that another relationship we could say in our notes, that the temperature inside the tank is equal to the temperature that leaves the tank. The temperature in the tank is equal to the temperature that leaves the tank, the water that leaves the tank. And this is also equal to the enthalpy out. These are all the same values. So I can rewrite this as our temperature as it leaves, which is the same thing as the temperature inside the tank, times our flow rate out. And there you go. So something also important to know, we're working with water. We're working with water, and it's in its liquid state. So we know that just as a law, or just a relationship in general, that for specifically liquids and solids, these two terms, our heat capacities, whether at constant temperature or constant pressure or constant volume, for specifically, now for gases, they are not equal. But for liquids and solids, which we're working with a liquid, heat capacities are the same whether they are at constant pressure or constant volume. So, yet again, another relationship right here. We can see that our heat capacity at a constant volume is equal or the same thing as our heat capacity at a constant pressure. And I forgot to write it in here, so it's not very clear what I'm saying here. Sorry. This is all multiplied by a constant pressure. Sorry. So, based on what I've said here, we know that it's working with a liquid water. These two are the same. So like our densities, before we've been canceling out, we can cancel out our heat capacities. Cancel out our heat capacities here. We're almost done. So now we are left with an equation that, after simplifying, is very similar to our equation which we had before in our other previous video when we were doing it in terms of concentration of a solute. So we have it in terms of a small change in our height times temperature. So right now, let's go ahead and divide across by our area. Let's go ahead and divide by our area. And we'll do chain rule real quick. And let's go ahead and separate this. So with chain rule, we can say that this changes into, let's go with our height times a small change in our temperature divided by a small change in our time plus our temperature times a small change in height divided by a small change in time is equal to our temperature coming in times our flow rate coming in. Let's make this a little smaller to have some room. Minus our temperature, which is the same as the inside of the tank and on the outside of the tank. So our temperature of the water leaving times our flow rate of the water leaving divided by our cross-sectional area. We want to get our small change in temperature with respect to small change in time by itself. So let's go ahead and subtract our term right here to the other side and bring it over. So this is going to go minus a temperature times a small change in height over small change in time on the right side, which leaves us here. And all we have to do is divide this entire thing by our height value, and now we have our term by itself. So our final equation is this. Let's go ahead and write it in a more simplified term, or more easier to see term here. So our last equation, which we just derived, is a small change in temperature divided by a small change in time is equal to our inside here. So our temperature coming in of the water times our flow rate of the water coming in minus the temperature of the water leaving times the flow rate of the water leaving. And then that is all divided by our cross-sectional area minus our temperature times a small change in the height divided by a small change in time. And this entire thing is divided by the height of the water. And that is our final equation. And gives us our two equations in which we can plug into Python and actually generate some plots about varying height and varying temperature over a 100-second time interval. All right, I think that's all of it. So thank you so much for watching. And let's jump over to our Python and do our last bit of the coding. Okay, so now we are going to take the equations which we just drove for the temperature and height of the water, and we are going to now plot them, and we are going to plot them on a time interval of 0 to 100 seconds, and we are going to show where they reach their steady states and how long it takes them to reach those steady states for height and temperature. And so really, the coding for this is exactly the same as I showed you before, the relationship, the four equations which we got in the previous video I did, when we did a similar problem dealing with height and concentration, mixing concentrations. We are now dealing with height, which is the same equation, and the mixing of temperatures of water. So we can really use the same code that we used previously for the concentration problem and just change the variables and the inputs. So if you see here, we can keep all the numpy and the integrate, all the functions that we call in, the things we call in here at the top. And we can go in, we keep the time, the cross-section area stays the same, and now the initial height is still the same. Our Qn stays the same. Our T of 0 is actually now our T initial. Our T initial for this problem was, I believe, 300 Kelvin. And then our temperature coming in, the water coming into the tank, was 325 degrees Kelvin. And everything else stays the same here. So now all we have to do is go down to these equations and substitute out whatever was the concentration and change in for the temperatures. So now we have our height equation stays the same. So our small change in height is equal to our flow rate in minus our flow rate out, which is alpha, 0.4, times our height, which stays at 1 meter. And that square root of that is the same thing as taking it to the 1/2 power, divided by our cross-sectional area, which is 1 meter squared. And now our small change in temperature is equal to our temperature coming in times its flow rate coming in minus the temperature inside times our flow rate out, which is alpha times, which is 0.4 times our height, like I said before, divided by our cross-sectional area, and all of that. So then we take and subtract out our C, which in this case is now temperature, and we take and multiply by our small change in height and divide by our height. Okay, so now we change out our numpy array here in the return function. Come down here to this part, and let's see, our right-hand functions now change correctly. Our C of 0 needs to be T of 0, and then everything else stays the same here. Change our concentration to a temperature here, and we'll change our concentration down here to a T, or for temperature. And let's make sure we run all these sections. And let's go ahead and change this. I found a mistake, and this will now make our plots dark. And all right. I'm not sure why it wasn't making it dark now, but I mean, there you have it. I mean, right here, like before, we have our plot of, on the left here, our height as it reaches its steady state over a time interval of 0 to 100 seconds. And we have our temperature as it goes from 0 to 100 in 100 seconds. over 500 points for both of these. And as it reaches its steady state. So here are two plots side by side, and there we have it. Thank you guys for watching and have a great day.